behind the scenes, guys. Fine. We have $28 for the winner this evening. Who's going to be the winner? Let's see who's going to be the winner. We got to pick. We got to pick. We got to pick. Yes, of course. I think.
I have Alan pick it. Let Alan do it.
There's a long story behind it. Oh, we won't even read it. We know the story. Oh, we know the story. Alan, would you like to pick the winning ticket?
So which one gave me the $2 was recognized as that?
Thank you. Okay, the winning ticket is 5049796. Did you get them? I didn't get some. Oh! Gary. Yeah. Come on, Gary. Okay. Thank you very much. All right.
Now we got 8, 9.
All right, now listen, guys and girls, right? Guys and girls. If you need to have a conversation, please leave the room. All right. With respect to our guest speaker this evening. All right. I just want to let you know this man, Alan Walkie, is the electronics RF field application engineer. Okay. He's not just some guy we met on the street and brought him in. It's not going to be that. I got to ask you, when you guys ask Alan W2AEW, when you ask him his call, all right, I'm not a ham.
It's an old call. It's old. It's older than my father.
So it was your father's call?
No, it's my initials.
Oh.
So, I figure when I get old and stuff's leaking out of my head, I'll still be able to remember my call.
All right, well, that's part of the answer then. So if you really know people's calls, like, oh, yes, we ran tube on 2 meters 6 years ago.
People by their calls and not by their names.
Yeah.
It's like a last name, like Bill W2 whatever.
Yeah, exactly.
Yeah, it's like a last name.
KC2RU.
Okay. I do want to also mention, you must tell everyone, we met a couple of years ago at a swap tailgate. That was the first time we met.
Okay.
And you were wearing a T-shirt of all the YouTube videos you had on you.
At the time, yeah.
Yes, you did.
Yeah.
And I was mystified about why you were doing that. And then you told me something I'd never known, that you actually had monetized YouTube videos, which now we have a couple of members also are putting out YouTube.
Well, I did it because Bob told me, did you know you could monetize your videos? I didn't know.
Are you serious?
Yes.
It's all my fault. I'm really sorry, Rich.
Yep.
Yeah, I did it.
Okay.
But Alan he has a significantly bigger viewership than I have, so.
How many subscribers do you have?
I got almost 52,000 subscribers.
Wow.
Close to 6 million total video views.
Wow. And how many videos do you have?
251, I think.
Something like that.
What is it, porn?
That's about right.
Is it all on scopes? Seriously.
It's all on, it's everything from basic electronics,
Electronics and stuff.
circuit tutorials, repair videos, test and measurement techniques, oscilloscope stuff, spectrum analyzer stuff.
You've done Arduino stuff and
some Arduino stuff, mostly analog electronics.
yeah.
And it's all with naked women pointing on the
But yeah, that's it. So youtube.com with my call sign.
Brother,
Please look it up and subscribe, okay, guys? And as you know, I've told everybody, you've got to subscribe to our own Radio Wild, Bobby Bennett's channel.
I just have a mere 461 subscribers and maybe 100 and 165 videos, I think.
But Bob is videotaping with my camera, so if this all comes out good, this will be on my channel later on. So,
All right, so please, pay attention, you're gonna learn something.
all right.
Thank you.
So thank you very much, and thank you guys. The only thing I ask is no snoring. Try to keep everything interesting here. So again, if you want to go take a look at some of my videos, that's my channel right there. I do work for Tektronix. I've been with Tektronix about 10 years. Basically an analog design engineer at heart. I've done for 25 years before joining Tektronix. So I've been a scope pilot for a long time. So, was it about 4 years ago we did scopes for dopes?
Yeah.
That info age? So,
I think it was 2011, I think.
okay, so, and that was, what I'm going to cover is reviewing a little bit of what we talked about in that class to kind of bring everybody back up to that same speed again. And then we'll talk about going through and looking at some of these signals in these radios and how you set up the scope and things like that. So, first thing I want to ask is, who's got the scope? Okay, good. Hands down. How many of them are sitting under the bench collecting dust?
Right now.
Yeah, that's okay. So, how many are afraid to use it, don't want to use it, that kind of a thing? Don't want to make sure you don't blow anything up when you connect up.
How many have more than one?
Yeah, well, I've got about 7 or 8 of them myself. So.
I only have 3, but.
Okay. But it's an addiction, But you guys got all the radios, I got all the scopes. So the idea here is to get you familiar enough to know what the basic controls do on the scope, and understand what it can show you inside these radios, and what to look for, what settings to use, how to hook it up, how not to hurt something, that kind of thing. So that's what we want to talk about today. Okay. And again, this is really for you guys. If you got any questions as we go along here, stop me and let me know, because I want to. I'm not here to just listen to myself talk. I want to make sure that I give you guys information that you can use. Okay. So today's agenda, again, just reviewing the oscilloscope basics, what the basic controls are for controlling the display, controlling the vertical aspects of the scope, and how we adjust that, how to control the horizontal aspects of the scope, and triggering controls, which are probably the most confusing thing for people. We'll talk a little bit about that. We'll talk about probes, why we use them, what they are, and we'll talk about safety, especially when it comes to dealing with tube circuits and big plate voltages and things like that, and the fact that where is ground and that kind of thing. We got to worry about that. And we'll do this using this really nice kind of trainer that Al provided to me. It's a typical All-American 5 type of AM radio. So we'll be able to look at some of the signals in the power supply and mixer and converter, IF detector, and AF stages within that radio. And we'll take a look at how do we set up the scope, how do we go look at that, so this way you can go see what they are. Most of you guys will restore radios and things like that using nothing more than a multimeter, and I think that's great. But sometimes you get the tricky problems, and you might want to go in and actually see what's going on with some of those signals. Okay, so that's why we want to talk about scopes. So what is a scope? Now I'm going to talk mainly about kind of analog scopes like these guys here. I do have kind of a newer fancy digital scope we can talk about later if we want to. But I figure if you guys have got scopes sitting on your bench, it's probably something more like those and not like this. Okay, I work for Tektronix, so I get to play with the cool toys. So, but on my bench, I've got those too. Okay, but I really like using the old analog scopes. Okay, so we're going to use this one here because when Bob brings the camera over to it, these settings for horizontal and vertical and things like that are right on the screen itself. So you'll actually be able to see that. So he's, okay, he's looking at that. We need about 500 millivolts of division vertically to see those type of things. Where it's a lot easier to see than where the pointer is on some of these older scopes. Okay, so that's why I brought that one in. So what do these old analog scopes do? How do they work? So it's basically like a TV, right? Where we're sending an electron beam down a tube, and what we display on the screen is really just how voltages change versus time. All right, it's kind of like if you took an analog voltmeter, put a pen on the end of it, and then ran a piece of paper like a chart recorder. That's essentially what an oscilloscope does. It just traces out voltage variations as the beam is moved across the screen. So it's just a graphing voltmeter, if you think about it that way. So we've got controls to control how the beam gets deflected up or down in response to the input signal. We've got controls to control how fast that beam moves across the screen to display that waveform. Okay, the faster the waveform, the faster we need to move that beam to spread the waveform out to see it. Okay? So we'll talk about the various controls that we use to do that and set up the scope to measure particular signals. The screen itself has got a number of divisions on it, and we'll refer to a number of the settings by division. Like let's say a vertical control, we're going to set it to 100 millivolts of division. What that means is the beam will move one division for every 100 millivolts you apply to the input. Okay, so I got 100 millivolts of division, I got a signal that occupies 3 divisions, I know that signal is 300 millivolts peak to peak. Right? Same thing with the horizontal divisions, we're going to talk about that in so many milliseconds per division, or so many microseconds per division. That's how fast we're moving the beam across the screen. Okay, we can use that to measure frequency, kind of not the most accurate way to do it, but it's one way to do it. So the major divisions, and it's typically 10 by 10, or sometimes it's 10 by 8. Those are the ones that we'll talk about in terms of divisions. There are subdivisions that allow you to make the measurements a little more precisely. So we set the settings on the scope according to these major divisions. Okay? So the display system, we've got a couple of controls that kind of deal with that. Basically, there's a trace rotation, focus and intensity. Focus and intensity are kind of obvious. Beam finder is one of those handy ones where the waveform is way off the screen somewhere. The beam finder will reduce the deflection voltages to kind of bring that thing on screen so you can kind of tell where it is. So you can adjust your controls to get the waveform back on. And I just kind of showed a couple of what some of these things look like. Illumination is typically for the scale illumination, okay, to light that up. Focus and intensity are going to be on the beam itself, kind of obvious controls. Trace rotation, we use magnetic deflection here, so depending on where the scope is and the magnetic fields in your house, sometimes the trace might rotate one way or the other. It won't be flat across the screen. The trace rotation allows you to correct for that. And if you move the scope to the other side of the bench, you might have to do it again. Okay? So that's what the trace rotation is. Doesn't mean there's something wrong with the scope, but doesn't mean you have to go in there and turn it. Just adjust that trace rotation thing. Okay? So those are the basic controls for just brightness and visibility of the screen. Simple things that are usually grouped together. Okay? It's pretty simple. Okay? The vertical system. This is one you're going to use probably most. And what this does is controls how many volts does it take to move 1 division or 2 divisions or 3 divisions on the screen. Okay? You've got an input signal coming in, and there's a number of controls that we use to process that signal as it comes through. Okay, amplify it, attenuate it, move it around, change its position, that type of a thing. So we've got a coupling control that we'll talk about in a moment, a volts per division control or sensitivity control, a position control, where we're going to place that trace on the screen, up or down, a mode control, because sometimes we'll have more than one trace. How do we want to interlace those 2 traces? How do we want to work with them? Okay? So those are the controls we'll talk about that go into the amplifier that drive the vertical deflection plates that move the beam up or down as it's being swept across. Okay? So let's look at some of those controls. Am I going too fast? Am I good? Okay. I know I'm not going too slow, so nobody's snoring yet, so we're good. All right, so the vertical scale and coupling controls. And again, I put a bunch of them up here. Depending on what scope you have, you might recognize, oh, that looks like mine, or that one looks like mine. That's why I put a bunch of them up here. So let's first talk about coupling. Okay? AC coupling or DC coupling. Now, something I want to make kind of clear is that when you're using a multimeter to make some of your measurements, you've got, AC volts or DC volts to make AC measurements or DC measurements. Okay? On a scope, AC or DC coupling doesn't mean that I use DC coupling to only look at DC signals and I use AC coupling to only look at AC coupling. That's not what it means. Okay? Oftentimes we might want to use AC coupling on signals that primarily have DC content and vice versa. We'll talk about why here. Well, what it refers to is how we're going to process that signal from the input connector to go to the amplifier. Now let's say, for example, I want to look at ripple on a power supply. Okay, I've got a B+ line that's sitting at 95 volts. Maybe it's got 2 volts of ripple on it. If I DC couple the scope, right, I might have to set it to 10 volts of division, so that 95 volts is about 9.5 divisions. If I've got 10 volts of division and I want to look at that little 2 volt peak-to-peak ripple, it's going to be this tiny little wiggly thing at the top. And you can't see it. You might adjust the position of the trace down and maybe go down to 5 volts of division, and I can still see it. And you adjust it down one more time, and now I can't adjust the position down far enough anymore because the signal's above the screen. So what you do is you use AC coupling. AC coupling throws a capacitor in series with that, blocks the DC, but the AC passes right through. Now I can adjust I can adjust to a half a volt per division. Even though I've got 95 volts DC, I blocked the DC. Now I'm just looking at the AC content. Makes it real easy to see that small AC content sitting on top of a large DC offset. So AC or DC coupling doesn't mean that you're looking at just AC or DC signals. It really determines how do I want to process that signal. And to be quite honest, most of the time we're going to be looking at signals inside of a tube radio. We're going to be using AC coupling. Because all we care about is what the wave shape looks like. We know what its DC offset is. Right? We can measure that with the voltmeter. Right? We want to look to see if the waveform is distorted in any way. So just eliminate the DC, go to AC coupling, and look at those signals. Okay? So that's what the coupling is. Now the volts per division setting is sometimes called the vertical attenuator or vertical scale control. You can see here it says volts per div, volts per div. On this one it says vertical attenuator. If you've got a scope that says vertical attenuator, it's a pretty old scope. It's what we call an old recurrent sweep scope, but they're generally uncalibrated. These guys are generally calibrated in so many volts per division. Okay, so there's another one here, volts per division. Okay, so that will just determine obviously how many volts it takes to make the waveform, so you can make those measurements. Now one thing you want to note is the scope's input impedance. It's typically printed by the input connector. This says 1 megohm and 20 picofarads. Okay, this one says 1 megohm, 25 picofarads. This one could be 1 megohm or 50 ohms, depending on what you set it to. Okay, and you also notice here's the coupling, AC or DC. Okay, here's coupling on this one, AC or DC. Okay, coupling AC or DC. Okay, so all of these scopes will have these various controls. You pick which ones you need for the measurements you need to make. Okay. The reason I want to say note the input impedance is that later on when we talk about probes, the probes can be adjusted to compensate them to match the frequency response of the scope. And the probes themselves will have a range of input capacitance that they can compensate over. So if you get a probe that can only compensate from 10 to 20 picofarads, and I've got this scope that's got a 25 picofarad input, it won't be able to be properly adjusted to use with that scope. We'll cover that in a little bit. Make sense, Phil? Okay. But that will typically be printed, on the front panel. Okay. Typically, the maximum input voltage will be printed as well, so it's good to take note of that. So there's a lot of good information on that front panel. Someone has cleaned it off. Okay. So, all pretty clear on the vertical controls? Okay. So, vertical modes. This is typically if we've got more than one channel that we want to display. There may be some good reasons for that. You might have two signals you want to compare. Maybe the input to an amplifier stage and the output to the amplifier stage. Is the signal inverting, so you know it's an inverting amplifier? Is the input clean and the output distorted? That type of a thing. You can compare those things. You can compare the volts per division. Each one can have two different volts per division, so you can actually measure gain by measuring the input amplitude and the output amplitude. So there may be good reasons to have two channels or more. Okay. When we're displaying those two channels, most of these scopes, the vast majority of them, are just a single beam scope. It's a single trace. So how do I display two traces, or two different channels? The answer is you use one of these two modes, one called alt, one called chop. Alt, or alternate, means that we're going to switch and display trace 1, trace 2, trace 1, trace 2 on alternate sweeps. Okay? And normally the sweep is going fast enough that you don't notice that. Okay, it flickers back and forth between them, but there's enough persistence in the phosphor that everything looks like, they're both just running all the time. When you slow down the sweep speeds to something a few milliseconds or more per division, you might start seeing them flip, 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 flip. Right? If we go over to the scope here, for example, and let's put on a second channel, so you can see that second channel there. And let's see, let me go to my alt mode and slow down. You can kind of see it's showing one, the other one, the other one, the other one. Okay? So that's where the chop mode, what that does, chop basically, while the sweep is happening, it's bouncing back and forth between the two pretty quickly. Okay. So that it looks like I've got the two traces going on very quickly, but what it's doing is it's tracing one, then flopping down, tracing the other, tracing the first one, tracing the other one, bouncing back and forth, and you don't really see it. It's chopping back and forth between the two. So you use chop mode when you have more than one trace at these low sweep speeds, but at the faster sweep speeds, you can go to the alternate mode. That's why there's two. Okay? So that's what they mean. I'm going to turn off channel 2 there. Okay? So there's these other two controls, add and invert. You say, well, why would they really be useful? Why would I want to add channel 1 to channel 2? Well, oftentimes you don't. There aren't really many applications where you really want to add the two, but what can be really handy is to subtract the two. Right? Because subtracting the two allows you to measure the voltage across a component. Right? Measure the voltage here minus the voltage here tells me the voltage across that component. Well, I don't have a subtract function, but I've got an add and an invert. So if I invert channel 2, then I add them together, that's the same thing as doing a subtraction. Okay? So the add and invert, so here's my invert and add. So I invert channel 2 and add the 2, it's the same thing as doing a subtraction of the 2. And a good example where that could be useful is on the audio output stage. Okay, driving the primary of the output transformer, that B plus typically has got a couple of volts of ripple on it. Okay, so it's before the bigger ballast resistor for the rest of the B plus. So if you just look at it with respect to ground, you got a big ripple and the audio riding on top of that. But if you probe that signal and you probe that B plus that's bouncing around with channel 2, inverted, subtracted, the result is just going to be the audio. Pretty cool?
Yeah.
Okay.
I didn't know that. That was cool.
So that's that. So this is a really handy thing to measure something, the voltage across a component. Okay. And the reason for that is we're going to talk about this in a minute. We'll talk about safety. Is that the big difference between this and this is that you can put these two probes anywhere you want. You want to measure the voltage across a component, you put the probes across that component. Right? Because this is completely isolated. The scope doesn't work that way. Okay, if you look at the scope probes, right? You got the probe connector there. It could be a little hook, it could be whatever, and you've got your other lead here. That's ground. So I can't just place that across any component because that connects ground to wherever you put it. Okay? So that's the big difference, and that's why this difference mode can be really handy because I can't just clip this across my component. There are special probes called differential probes that allow you to do that, but that's not most of the probes that you have. Okay? So we'll go play with that in a little while too. All good? Okay. All right, so let's take a look now at the horizontal system. The horizontal system is what moves the beam from one side of the screen to the other. Okay, how quickly do we move it? And again, we're using magnetic deflectors, so we're essentially applying a voltage to these plates that are pulling the beam from one side of the screen to the other. And then very quickly retracing it back and doing it again. Okay? So how quickly we move that is controlled by this little sweep generator. And that has controls for number of seconds per division, milliseconds, microseconds, nanoseconds, et cetera, per division. And there's some trigger controls and some mode controls to talk about with that. And there's a trigger that's going to get into that too. We'll talk about that in a little bit. But the bottom line is that generally the scope is moving that beam back and forth. There is another mode in the scope we'll also mention called XY mode. And this is where, say, channel 1 could drive the vertical, and channel 2 can drive the horizontal. So rather than having the horizontal driven by the sweep generator, we have the horizontal driven by another input. And there's some applications for that too. We'll talk about that. Okay. So sweep control is often called the time-based, okay? Or on the modern digital scopes, it's called the horizontal scale, because there's no sweep on modern scopes, right? So I remember I'm an application engineer for Tektronix, right? We make oscilloscopes and a lot of test equipment, and I had a new young sales engineer came in, and I said, oh, well, adjust the time, make the time base faster. And he goes, where's the time base control? Like, horizontal scale, okay? Horizontal, never used an analog scope before, so I didn't know what the time base was. So, but it can do. So when we talk about sweeping that, there's actually two ways that works. There's these old recurrent sweep scopes. If you have one, get rid of it and get a more modern one like these. Okay?
Is this a sales pitch?
No. I'm not even saying buy that. Get one of these. Okay? Because the problem is the recurrent sweep scopes, what they do is they have a free-running sawtooth oscillator that's driving the horizontal beam. But it's a free-running oscillator. So when you put a signal in there, the signal, if it's not perfectly locked or synchronized to that signal, it looks like your signal's walking back and forth on the screen, right? It's not steady, okay? In some cases, that's fine. Like if we're just looking at an IF waveform like this, who cares? Right? We're not really wanting to be triggered on it, so that works. And there's usually some kind of a lock control where you can kind of try to injection lock your signal to the sweep, and there's some vernier controls to kind of get it. Nothing's calibrated, but today, you know, these scopes, like this scope here is, you know, over 30 years old. You can buy something like this for $100. There's no excuse to hang on to these old recurrent sweep scopes anymore unless you like the technology. Okay, but it's very older, simple technology. What we're talking about with these scopes is a triggered sweep. We still have a horizontal ramp that drives the beam from left to right, but the horizontal ramp is kicked off by a trigger. Okay, so the trigger circuit says, send the sweep now. And then it goes back and sits and waits for the trigger again and sends it again. Okay, so if we give it a trigger that's synchronous to your signal, now the waveform is stable. So that's what we're talking. We're going to talk about trigger here in a moment. But they generally have a calibrated sweep time, and they're more flexible and powerful than the old recurrent sweep scopes. Okay? And typical controls, you'll have a wide range from seconds per division up to microseconds or even nanoseconds per division, depending on the speed of the scope. Okay? Typically in a 125, 125, 125, 125, and then 0.1, 0.2, you know, that kind of a thing, type of a thing. And there is a vernier control if you want to get a variable on it, but generally you're going to use the calibrated knob, if you will. Okay? So the key here is if we're going to use this trigger sweep scope, is we're going to use a triggering control. Okay? So what is triggering or synchronization? It allows us to stabilize the waveform so we can view it and actually look at its characteristics rather than have it sliding back and forth on the screen. Okay? So it typically locks the sweep rate to some feature on the waveform. So that each time I do a sweep, I sweep this section, the next one I sweep that one, next one I sweep that one, all those traces lay on top of each other, and it looks like the waveform's stable. Okay? If we weren't, we're just randomly sweeping different spots, the waveform would look like it's moving back and forth, kind of like the wagon wheels turning backwards in the old westerns. Same reason. Okay? Again, these old recurrent sweep scopes will generally have an external sync amplitude, okay, or an internal sync selector, and this amplitude basically takes a piece of that input signal and jams it into the horizontal oscillator to try to make it lock or pull it and lock it to it. Okay, really ugly, doesn't work very well. Okay, and it's the only control you have. Here's my comment on that. Okay, whereas the trigger sweep scopes allow you to set up a particular trigger criteria. What do I want to trigger on? Rising into the signal. When it rises past a certain voltage point, so when that happens. Very simple. Much more powerful and has a lot more capability on the trigger controls. So let's dig into that a little bit. Now most of the time you're going to use 2 or 3 different trigger settings on your scope, and that's about it. So let's kind of explore what some of those things are. Okay. So the trigger source, what are we going to be triggering on? Most times you're going to have it set to internal, meaning I'm going to pick off a piece of the input signal and trigger on some aspect of that input signal. Okay, so internal means I got a signal coming into channel 1 or channel 2, and I'm going to pick off a piece of that, or make some adjustment on that and say I want to trigger whatever that signal, which is already in the scope, is doing something. That's internal triggering. Okay. External triggering refers to, like maybe an external input, okay, that I'm going to bring the signal into and use that as my trigger source. It might be somehow related to the other signal without going into the other input. You're probably not going to use that one much at all. Line triggering, who knows what line triggering is?
60 cycle.
Triggering a 60 cycle line input, exactly. Now where would that begin? You want to look to see if there's any particular aspect of your signal that is synchronous to your ripple and your power supply. Okay, or something else going on the 60 hertz line. So that way, it's a real simple thing. If I know I'm looking at ripple, or I want to look, or maybe I'm looking at an IF signal, and there's a little bit of ripple on the B+. So if I look at it, it's kind of moving all around back and forth. If I go to line triggering, I might get just a slanted portion of where I'm looking at a portion of the ripple, but it's stable. Because I'm always looking at the same portion of that because it's synchronous to the line. So it can be handy to help you look at signals in the presence of ripple on your power supply, okay, because it'll stabilize the ripple, and you can look at the waveform just riding on the ripple, okay?
Okay.
So handy thing, for that. Trigger mode, okay? Okay, now I know what I'm going to trigger on. How am I going to use it? What auto trigger does is not what you think, okay? It doesn't automatically set up a trigger for you, okay? What auto trigger does is it looks for the trigger condition that you've set up on the controls, and if it doesn't see an event that you've set up, like if I didn't see a rising edge that crossed 5 volts, it's going to send the sweep anyway, okay? Because if you don't do that, if you go to normal trigger, if you set up the trigger controls that aren't being met by the input signal, the sweep never happens, and the screen is blank, and you have no feedback of what's going on. So auto trigger set is going to look for that condition, and if it gets impatient, says, you're not giving me a trigger, I'm sending a sweep anyway. But it allows you to get something going across the screen so you can see what's happening. Maybe you got to adjust the trigger to go see it. So auto trigger is where you're normally going to leave things, okay? And you could use normal trigger, but most of the time auto trigger will be just fine. Single trigger you'll probably never use, okay? It just sends a sweep once and then stops. It only is useful on these scopes if you've got a scope camera attached to them, okay, to kind of catch that event, okay? And TV triggering, some of the scopes you'll see TV line triggering, and that triggers on NTSC signals to pick out a particular line or something like that. So you're working on TVs. This is useful. If you're looking at a video signal, this can pick off the horizontal and vertical sync pulses and trigger on those things. So that's what those are. If we're working on the radio stuff, ignore these guys, and probably even that one.
Right. Yeah.
Just use auto on. Okay? Make sense? All right. Trigger coupling. Just like on the vertical input, we can take this signal that we're sending to the trigger circuit and AC couple it or DC couple it. Okay, so again, if we want to remove the DC content, we can AC couple it, just trigger on the ripple portion or whatever, the small DC or small AC portion riding on top of the DC. Some other scopes will have other coupling modes like HF reject, which is high frequency reject. So you got a low frequency signal with some high frequency stuff on it. I want to trigger on the low frequency portion of it. The HF reject is a low pass filter that will get rid of the high frequencies. But again, most of the time you're using one of these two. Okay? The easiest one is typically AC coupling. But if you're looking at digital signals, that might stay 0 for a long time and then go to 1. AC coupling really won't help you much because that'll settle out to that DC value, right? So depending on the duty cycle of the signals, how much whether they're balanced or not or whatever, audio typically AC coupling is just fine. DC coupling for cases where you know you need it. Okay, but you can probably you can play with the others, but auto coupling, AC, internal. And what's handy is, and a lot of scope manufacturers kind of did this. If you look at this scope here, the trigger controls over here. Okay, let me get my glasses on. Sorry. Okay, or I'll look at that. So if you look at this, focus up on this scope here, Bob.
Okay.
Okay. If you look here, there's trigger mode, right? You can see at the very top it says auto. The next one says normal. The next one says single. Here's my trigger coupling. Top is AC, then low frequency reject, high frequency reject, and DC. Okay. And source, channel 1, channel 2. In this case it says norm, which is the same thing as a normal trigger, which is internal trigger. But what do you notice about this? One of the most common ones I told you to use. Auto,
Yeah.
AC coupling,
Right.
and internal trigger.
Internal trigger.
All those are at the top of the controls. Take all the trigger controls, bring them to the top. Okay? So most old Tektronix scopes are like that, and a lot of other manufacturers copied that kind of convention. Just bring all the trigger controls to the top, and you're kind of set up to auto trigger, AC couple, internal. And you're good to go. Okay? So let's talk about the most common controls you're going to use are just doing a simple edge trigger, trigger on a rising or falling edge of a signal. Okay, so we're going to trigger when the voltage on that signal comes up through a threshold and then kick off the sweep. Or I'm going to trigger when the signal falls through a threshold and kick off that sweep. Okay, so that's some scopes call it the slope or polarity. Okay, positive means that this voltage is coming up. Okay, when it crossed this threshold here, then I start to kick off the sweep for that waveform. If I flip it down to negative, now I've got this voltage that's coming down, crossing that threshold, and then kick off the sweep. So that's what the slope means. Okay? In most cases when you're working on stuff, you don't care. but you might, depending on what waveform you want to look at, you might want to worry about it. And you can adjust that level up or down. So if I take that voltage level, okay, and I move the level back and forth, and I move that level from this positive position here, and I turn that knob to negative down here, you can see that I'm triggering on the lower voltage level down here. Okay.
Okay.
So that's how those four controls work. Positive or negative slope, level up or down. And again, what you can do is flip the switch up, okay, to positive, and set your level control right to the middle. You have your AC coupling, you can be right in the middle of your waveform. And you should get a triggered sweep without a problem. Okay? With line triggering, you don't have to worry about those. It just automatically triggers on the line. It doesn't really matter what you set those to. You can change the slope, but the level control really won't matter. Okay? Make sense? Those four sets of controls, the display, focus and intensity, the vertical controls for scale and coupling, horizontal controls for how fast we're sweeping things, and trigger, are the only things you got to worry about. Okay, when setting up a scope. Oftentimes, when you're looking at signals inside of a radio or something like that, you kind of know what the signal's supposed to look like, right? I know if I'm looking at the beginning of an IF amplifier, that signal's going to be pretty small.
Yeah.
If I look at the output of the IF amp, or I look at the audio output, it's going to be big. So that tells me what do I need to set my vertical controls for. Do I actually want to see the local oscillator signal? I need to sweep fast so I can see the sine wave of that. If I want to look at something that's audio related, whether it's the variation, the amplitude variation of the IF, like we've been looking at here, or looking at the audio output stages, typically 1 or 2 milliseconds of division is pretty good to kind of look at the audio content. Okay, so but we're looking at the LO signal. It might be 1.5 megahertz, right? Because it's 455 kilohertz above the signal you're listening to, right? Where most of these things are high side injection. So you want to bring that all the way up if you actually want to see the sine wave. Okay, so if you're sweeping really fast, we stretch that sine wave out and you can see it. Right. So those are the controls you're going to worry about. So now we just have to get the signals into the scope. So we just go over and connect wires from the scope to the radio? Well, not quite. What I recommend always is using probes. Okay? A probe, just like we're not going to connect bare wires to something with a multimeter, we're not going to do that with a scope either. Probes allow you to connect the signal to the scope. They can minimize the loading of what you're doing. And the most common that you run across are passive probes that are called 1x or 10x probes. There are active probes and specialty probes we won't talk about. We're going to talk mainly about this. All right. So, in general, a 1x probe is kind of like a direct connection to the scope input, right? So it's just a convenient way of coming out to some connectors that are easy to connect up to your circuit that you're testing. Okay. Most of the time, you're not going to want to use 1x probes, though. There's a couple of reasons why. They don't attenuate the signal at all before it gets to the scope. So whatever voltage is there, the scope sees. So if you're working on stuff with some high B plus voltages, you got to start paying attention to what the maximum input voltage is on that scope, so you don't hurt it.
Hope you don't exceed it.
Hope you don't exceed it. Okay. But the bigger problem is they can have pretty excessive capacitive loading. Right. This is a couple of feet of coax. Right. So if I've got 20 picofarads of input capacitance on the scope. Okay, maybe I've got another 50, 60, 70, 80 picofarads in the coax. So this is like taking a 100 puck cap and connecting it to your circuit. Now, if you look at the audio output stage, probably not a big deal. If you're looking at a tuned circuit where the tuning caps are on the order of 20 picofarads, what happens if you put 100 picofarads in parallel with them? Okay? Everything mistunes, doesn't work, it doesn't happen. So most of the time you're not going to want to use 1x probes. Okay? Most of the time you're going to be using 10x probes. Okay? Now 10x probes, effectively at the probe tip, they've got like a 9 megohm resistor in series with the coaxial line. So that basically isolates all of that capacitance, but puts 9 megohm resistance in between them. So capacitance is much, much lower. Okay? So that's good. And we choose 9 megohms because that forms a 10x voltage divider between the probe tip and the 1 megohm input impedance of the scope. So we've got a 9 meg and 1 meg is a 10 to 1 voltage divider. That's why it's called a 10x probe. Doesn't make things 10x bigger, makes them 10 times smaller. Okay, so what it means is that the scale that you set up on the scope, if I set it to 100 millivolts a division, and I connect up a 10x probe, it's now 1 volt per division, 10 times bigger. Okay, the scale is 10 times larger. Okay, it's not 10 times more sensitive. Okay. So again, along with the scope input, it attenuates the signal. Good thing, it dramatically reduces the effect of capacitive loading on the scope. These 10x probes might have an input capacitance of 10 or 15 picofarads. That can still be a lot, okay, on some of these tuned circuits, as we'll see in a moment, but it's a whole lot less than 100 picofarads that you have with the 1x probes. Okay. The bad thing is they need compensation. We'll talk about that next. Okay, and so let's dig into that. So what is compensation? Well, here's kind of a schematic of what that probe looks like. There's the probe tip and the ground clip. There's my 9 megohm input resistor. There's my 1 megohm input impedance of the scope. Now, we said that 9 megohm, or the 1 meg is in parallel with, what did I say, 20 picofarads, 25 picofarads. So that's what the scope looks like. All right? So if I did that, what would happen is the frequency goes up. I've got an RC low-pass filter between that 9 megohm resistor and that capacitor. So the bandwidth of the scope, the probe, would go way down. Well, why the hell did I do this? Right? I just lost all the benefit that I had, right? So what we do is we put another capacitor in parallel with the input resistor and make the ratio of these capacitors basically the same or the inverse of this ratio. So at low frequencies, DC up to a couple of kilohertz, that 10x voltage divider is dominated by the resistors. As the frequency goes up, the 10x divide ratio is dominated by the capacitors. Okay, because the impedance of that capacitor and this capacitor at 2 megahertz is a lot lower than 9 megohms and 1 megohms. Okay, but if we scale these right and get that ratio right, we get the same voltage division. It'll be a capacitive voltage divider instead of a resistive voltage divider. So we got to get it right. And because every scope is different in terms of input capacitance, we have to be able to adjust that. That's probe compensation. So if you ever look in front of your scope and you see this little thing that says calibrator, okay, or probe adjustment, okay, you see this guy right down here, what does it say? This one says calibrator, and on this one these both say calibrator. Okay. What the calibrator is typically about a 1 kilohertz square wave. All right. Now, what are the characteristics of a square wave? It's got frequency components at its square. It's got frequency components at the fundamental and at odd harmonics.
Right.
Okay, so if I go to so if I got a 1K square wave, I got energy at 1 kilohertz, 3 kilohertz, 5 kilohertz, 7 kilohertz, all the way up. Okay, so I got a broadband signal that I can now use to compensate the frequency response of the probe. If I have the capacitors set up wrong so that the capacitive voltage divider is less than 10x, okay, at high frequency, I'll have an undercompensated situation where the high frequency content is rolled off. It looks like a low pass filter. Okay, so the edges kind of get rounded. You'll still get the lower frequency content, full amplitude, but the high frequency content, the edges get rolled off. That's called an undercompensated probe. Okay. If I turn the capacitors the other way, that voltage divide ratio might be greater than 10x at higher frequency, I get this situation, overcompensated. The high frequencies are accentuated, they're divided down by less than 10x, so I get overshoot on the waveform, undershoot on the waveform, overshoot on the waveform. So really what you do is, those little screwdrivers that came with your probes that you all threw away are stuck in the drawer, right? You connect the probe up to the compensator, and you adjust the trimmer on the probe to make the waveform look like that.
Yeah.
Right. Let me show you what I mean by that. We'll do it actually on one of these waveforms. Let me scoop out of the way because I think I got my screwdriver inside here.
You don't have your green Exolite in your pocket projector?
That'll detune it.
Oh, it's got to be ideally a non-metallic, non-metallic screwdriver or one with just a tiny little metal blade in it.
If that's 10 megs, that Exolite will take it off.
All right. So let's actually grab this guy here. Okay. And let me go into the calibrator over here on the scope. This one looks like it's pretty well compensated, doesn't it? So nice little 1 kilohertz square wave. So look what happens if I misadjusted that.
Curiosity, you only see one back.
Okay. There I'm
Now you're
overcompensated.
overcompensated.
Right. If I adjust that down, I'm undercompensated. Right. And if I adjust it just right, now I'm properly compensated. Now in square wave, it's really obvious. But if I was looking at, say, a 455 kilohertz, IF signal, and I was undercompensated, it would look like that signal was really small, but it gets a little past filtered. Okay? If I had it overcompensated and I looked at that LO signal or whatever it is, it might look bigger than it really is, because the scope was expecting it to be attenuated by 10x, and it's not. So you want to properly compensate your scopes. Go find your screwdriver, compensate your probes. Okay? It's amazing how many professional engineers that I run across over the 25 years when I was a design engineer and now the 10 years that I've been in Tektronix that have never compensated with things.
Anybody got a greeny X-light here? Show them what it does to that wafer when you touch the trimmer.
Yeah, I don't have one. Put the trimmer in there and the waveform goes.
It goes totally fine. You tune it with that, and then you take the screwdriver away, and then it's back to rolling again.
Exactly right. So what's the lesson here? Compensate your probes.
Compensate your probe.
Use 10x probes, because what it does is it does reduce the voltage going to the scope by 10x. So if I've got a 200 volt V plus in the radio, the scope's only going to see 20 volts. It's not going to care about that, right? So always a good idea to use 10x probes. They have lower loading, and so they won't distort the waveform as much, and they'll also give you more
I think
sync.
they had a guy at Sussex selling them too. So 2 more weeks, get a probe.
Or you find some. But that's what that little trimmer is on it. On some probes, the adjustment is actually on the probe body. On other, adjustments might actually be on the probe handle, the probe body itself here. It all depends on the construction of the probe. You'll find some probes that have got the 1x, 10x switch on them, right? Glue it in the 10x position, don't worry about it. Okay, so something else to think about is that most scopes, or the inexpensive analog scopes, they don't know whether you've got a 1x probe or a 10x probe attached to it. Okay, so if you know you're using a 10x probe, you have to mentally know that you're going to change that scale. If I set it to 100 millivolts, it's really going to be 1 volt. Okay, if you look at a scope like this, focus on this one, Bob. There's actually 2 little lights that light up. I don't have it turned on, because these scopes will actually sense whether it's a 1x or a 10x probe, and it'll light up the number under the skirt appropriately. Okay, and the way it does that, if you look at these scope probes, you can see the little pin on the side here. Okay, I'm clicking with my finger. I don't know if you'll be able to see that little pin there. Yeah, you have it there. There you go. That little pin.
There it is.
That pin contacts a ring here, and there's a resistor in there that tells it, hey, that's a 10x probe. Now, if you look at the scope here, you see that says, what does that say, 20 millivolts of division down in the corner there? Okay. How do I connect the scope up? The probe. It just went to 200 millivolts of division. It knows. A lot of scopes won't know.
That's a smart one.
Right. This is a smart one. A lot of scopes won't know, so you have to know. Okay, so that might explain why, hey, I measured this voltage, it's 10 times bigger than it should be. I'm using a 10x probe, that's why. Right? Okay. Because your scale isn't what you thought it was.
Alan,
Yeah.
I think that'll applicate with you. Tektronix probes,
Yes.
Chinese probes.
In general, you get what you pay for. Okay? In most cases, I mean, for what we're doing here, you can buy a $10 probe on eBay or Amazon or something like that, and it'll work fine. It may not hold up for some of these probes are 30 years old. It may not last 30 years, but it's $10. They don't care. Okay? And the frequency response might not be perfectly flat. But again, for what we're doing here, we're looking for, hey, is the signal there? Is it distorted or not? It'll work. Okay? So that's the real key is if you're looking for a probe to match your scope, the probe will have a rating on it over what input capacitance range can it be compensated for. So we'll say the compensation range might be 10 to 30 picofarads or 15 to 30 picofarads or something. So you have to kind of know what your input capacitance is on your scope right on the front panel. So buy probes that can be compensated for that capacitance. Okay? So the one other mode that that I mentioned is this XY mode. And XY mode is where, say, channel 1 drives the vertical position of the beam. Channel 2 drives the horizontal position of the beam. Okay? Now, why would we want to use that? I mean, you can actually measure frequency. If you have a known frequency going into one and an unknown frequency going into the other, you can get these little lissajous patterns that you can count frequency ratios by the number of loops or lobes on the waveform. You can measure the phase difference between two signals. Okay? By looking at if both signals were exactly in phase, it's like an etch-a-sketch, turning both knobs the same way, you get a diagonal line, right? Just like that. Okay, if I turn them a little bit out of phase, I can get circles or ellipses and that kind of a thing. It's the same thing. It's an etch-a-sketch mode of this too. Okay. Not really handy, but there are applications where you can use something like that. This is kind of what it looks like if you hook up to the left and right channels of the stereo listening to Pink Floyd. Right? So that's kind of where that came from. Okay. So we've got frequency comparisons. You can do curve tracer applications. Actually, I have a couple of videos that show doing actual curve tracing. It's a little simple circuit, tracing out X and Y, curve tracing. So what's really useful for us is doing frequency response curves, sweeping an IF. If you've got a little signal generator that can sweep, okay, you can do a couple of things. You can set up that sweeping signal through your device, your radio, whatever you're testing, through the IF chain, whatever it might be. Probe the output, and then either, if the generator has a ramp output, so the ramp voltage is proportional to where the frequency is, have that ramp go into X, and the output of your signal go into Y, and you essentially can trace out the shape of your IF. Okay, and you can tune things in the IF and actually watch that move around. And this is a very dramatic example of very low frequency sweeping to a higher frequency over a kind of broadband bandpass filter, but you kind of get the idea. You can do that. If your signal generator doesn't have a sweep voltage output that corresponds to a sweep, sometimes they'll just have a sync or a trigger output. Okay, so you can set the sweep to, always sweep in 100 milliseconds or 10 milliseconds or something. And then set the scope up so that its sweep corresponds to the length of the amount of time you're sweeping the frequency. And then set the trigger to external, bring that trigger signal into the external input. So you trigger the scope at the beginning of the sweep, and every single sweep corresponds with the frequency sweep, and you can do the same type of thing. Pretty cool? So it can be pretty handy for that kind of thing. It's a little tricky to set up, but man, you can see the shape of your field. Not just peaking the magnitude of it, you can see what it looks like. So if you've got multiple tune stages, you want to kind of bias tune them a little bit to give you a little bit broader bandwidth versus having everything perfectly centered and narrow. You bias tune a little bit and kind of get a wider frequency response, that type of thing. So that's what one of the applications you can do more than advanced tuning using XY mode. Yeah.
Al Placement gave us a lecture on using a sweep generator to set up the LIS in a radio. But I was looking at some 1950s radio television news, and they had 2 articles on doing that exact same thing.
Yep.
And they said, setting up your radio that way separates the men from the boys.
There you go. And actually, the device that was pretty popular then was something called a wobulator. You've heard of a wobulator, right? So a wobulator is just an oscillator that can wobble back and forth. Typically, it's wobble back and forth at 60 hertz. Okay? Well, that's handy. 60 hertz, I can do line tracing on the scope. Okay? And I wobble the input and then just trace out what that signal looks like. And I'm synchronized to the line where I'm wobulating, and I can very easily do that. So that's kind of another way to do it. You might say, well, somebody's selling a wobulator. Now you know what you use it for. Get your scope out. Okay, so actually there's another little thing here. This little circuit, if you will, is called an octopus. Who's heard of an octopus before? Okay. So an octopus, a little filament transformer, a little series resistor, and we put one voltage across a resistor, one probe across your device under test. It's a little simple curve tracer, sweep diodes, capacitors, things like that. You can build this to a couple of handful of parts and do it. And if you ever use the Huntron tracker, it's kind of the professional version of an octopus. Okay, it's just a simple curve tracer to see how the diode is good or something like that. Okay, so that's another example where X, Y modes can be fun. So the scope control layout. Typically, the controls are laid out in a semi-logical fashion. Okay, all of the vertical controls grouped together, usually near the vertical inputs. Okay, position control, vertical scale. Okay, coupling controls, inputs. Okay, so vertical controls are grouped together here. There's channel 1 and channel 2 vertical controls here. Okay, vertical controls here and here grouped together. Okay, vertical controls here grouped together. So looking at the scope, it's not just a sea of buttons, it's kind of more logically arranged now when you look at it. Same thing with your horizontal controls. Horizontal controls here, horizontal controls here, and horizontal controls here, okay? Triggering controls there, okay? So everything is kind of grouped together. So just work your way through, like, okay, I know my signal is going to be about 2 volts peak to peak, I want to AC couple it, boom, boom. I know it's going to be an audio type signal, 1 or 2 millivolts of division. Pull my trigger controls up to the top, good to go. Start programming your signals. Okay. So most analog scopes are going to be laid out in a pretty logical fashion now. Okay, not even this. Okay. So how are we doing? Everybody good? Good. All right. So let's talk again. A little bit of word about safety in testing some of these old radios. I mentioned this earlier. Your multimeter probes, like my old Simpson 260 here, fully floating. I can connect the probes to any 2 nodes that I want. Well, I set the meter right. That doesn't matter. Nothing's connected to ground. The analog scope inputs are not that way. That input is not floating. One side of that probe, that lower ground clip, is called ground because it's ground. Okay? Now, a lot of these old radios are not isolated, so use an isolation transformer. What I did here, just to be even further safe, I connected from the ground connection on the scope to the ground connection here. So I tied ground together even before I attached the probes. So I make sure I don't do that. Now, everything was fully floating. I could connect ground wherever I want, but now you might force the chassis to some other voltage. Because now I made 90 volts be ground, so now the chassis are minus 90 volts.
But the classical screw up in the All-American 5 is where you burn the ground lead off the probe.
Yes. Well, that's the best thing that can happen, right? Otherwise, you could also hurt the scope. But if you burn the ground lead off and that was your fuse and told you, duh, I did something wrong, that was a good thing, right? So use an isolation transformer, establish a ground reference, and then from there you're just probing single-ended voltage with respect to that ground point. For any of the inputs, they're all with respect to that same point. Now, if I want to measure voltage across a component, what do? Invert and add. Right? 2 probes, invert and add. Okay? So again, one side's always connected to ground, always measure with respect to ground. Use of isolation transformers recommended, and use those 10x probes. It keeps the lethal voltages away from the scope input. Okay. And but that's the rest of it's common sense. You guys work on this stuff, and you know what to do. But when you're dealing with a scope, all these inputs generally are connected to the same ground reference. Okay. So there are some special scopes that have fully isolated inputs, but that's not the norm case. It's an exception. Okay. But generally all connected to ground. Okay. So, how do we take a look at signals inside an All-American 5 radio? This is not the exact schematic of the trainer here. Actually, I meant to do this earlier. This is actually a photograph of that trainer that I put into Paint Shop and inverted the video. So black is white, white is black. So now you can actually see what that is. So I made copies of this for everybody. I'm going to grab a copy and pass it around so if you want to follow along what we're doing. As you know, all the All-American 5 radios, everybody is a little bit different. Generally the same tube complement, but the circuits are similar, right? Yeah. And there may be some differences. So this schematic I actually got from another YouTuber, YouTube channel All-American 5 Radio.
Yeah.
You guys familiar with him?
Yeah.
Richard McWhorter. He's a great guy. Really good, really nice videos. Very smooth videos to make sure you get it. But he's a really good guy. Fantastic explanations, and his illustrations are phenomenal. Much better than what I do on my videos. So I asked his permission if I could use his schematic because everything was so well done and color-coded and everything here. So that's where that came from. Highly recommend Richard's channel if you haven't looked at it before. So what do we want to look at, right? So at the front end of the front end of the thing, okay, you can tell me what's going on in that first tube. And what have I got coming in here?
We got-
My RF signals,
Yeah.
right? What's going on down here? That's my local oscillator. So then they're getting mixed, so what have I got coming out?
Oh, yeah.
Oh,
Yeah, plus everything else.
At this point, right here, I've got IF, right, which is, LO minus my RF input, plus the RF input, plus the LO,
Yeah.
plus the sum and differences of multiples of those signals. I got signals all over the
Bazillion
place.
harmonics.
All right here in this current,
Yes.
right? Well, what's going to impress a voltage across this tuned circuit, right? This tuned circuit represents a high impedance only at their IF frequency. So all those other currents and all these other frequencies don't have a load to generate a voltage on. So the only voltage that gets generated across that first IF transformer, that tuned circuit, is at the IF frequency that you want, at 455 kilohertz. Okay, so that's generally what you're going to see if you probe this, because we're probing voltage, not probing the current. Okay? So that's what's going to appear there. But that might be pretty small. Okay?
Yes.
Generally, it's going to be, it depends on the LO drive and things like that, but it might be
Right.
pretty small. Okay. So then we've got an IF amplifier. That's going to take that small thing, make it a little bit bigger, but it's now still the amplitude modulated signal
Right.
at the IF. Okay, just a little bit bigger. But now what happened? Now the local oscillator is just a sine wave. Okay, you can kind of probe it there. But take a look at what's going on here. 2 to 10 picofarads, 2 to 17 picofarads. What did I say that scope probe, the 10x probe in capacitance was? 10 to 15 picofarads?
Yeah.
What happens if I put that probe there?
Each is set.
That places 10 to 15 picofarads in parallel with this 30 or
You
40
may not have an
picofarads.
oscillator anymore.
The thing is, it's on the same order. It's a little bit less than this capacitance. So it'll probably still oscillate, but it's going to shift up in frequency,
Yeah.
right? It's not going to shift down. It's going to shift down in frequency.
Well, yeah.
So it's going to shift down. When I increase the capacitance, it shifts down.
So it's going to bring it down.
So if I was tuned to a signal, I put my probe on here, I might not hear the signal anymore. But if I tune down, now I'll hear it, because I've just changed the components in the tank circuit. But if you're just looking to see if the thing's oscillating or not, you can do that. Okay, it's oscillating, take it off. Okay, so we'll kind of cover some of that again. And then we've got the detector. We've got to go through each of these sections. So Richard did a nice job in color coding all these things. So let's kind of walk through these stage by stage. Okay, and then we'll go take a look at it right on it.
You can kind of see the oscillator if you hold the probe close.
Yeah, a little loop. You can sometimes see it
Put
without
it at
affecting
the
it.
most sensitivity and just hang it near there. You
Okay,
can actually see the
Just
oscillator.
capacitively couple to it without really loading it down. Now this is the same page that I handed out. So this is what you're going to be looking at. This is the schematic of this trainer here. So this is actually what we'll go look at. Right. Let's first talk about the power supply. So that's the power supply on our trainer. Okay, this is the one from Richard's circuit here. So what we're going to have is right after the rectifier, we're going to see the half-wave rectified line signal. Okay, that's right after the rectifier itself. And then on the other side of the filter cap, we're going to see hopefully not too much ripple, but probably some. So let's actually go look at that. This guy's still on here, right? Yeah.
I think we ran out of audio.
Oh, okay. Well, that's okay. Let's for the power supply, we don't really care, right? So if we take a look, I kind of put up on here on the scope controls about where you want to be with settings. V, H, and T, vertical, horizontal, and trigger. Okay. So vertical, we kind of want to be AC coupled, and in the neighborhood of 10 to 20 volts a division. All right. Move over here so you get that on the screen there.
Sure.
All right. And about 5 milliseconds of division. Okay, so we're looking at something that's just 60 hertz. Okay, 16.6 millisecond time constant. So I connect the probe up here and get my glasses out so I know where I'm grabbing components. We look right after the rectifier. Okay, there's my half-wave rectified, AC line. Okay, make sure your diode's good, everything's good. Okay, all right. Now, on the other side of that cap, or the other side of that ballast resistor, I'm probing kind of on the one side of that 100 ohm resistor, it's right after the diode. Look at the other side of that, I'll be looking basically at the junction of that and the first filter cap. And that's the D plus for the audio transformer, right? For the audio output stage. If we go look at that, I can see a little bit of ripple on there. For ripple, I need to go down to about 2 volts of division. So now I'll bring my scope down to 2 volts of division. I'm AC coupled, so now I can actually still see them.
Right.
I didn't do it, but I could switch my triggering over to line triggering, so now I don't have to worry about that. In fact, we could let's take channel 2. We turn channel 2 on. I'll bring that to, say that's 20 millivolts, 20 volts of division, and let's set that to chop. And let's connect this guy up to the other side of the 100 ohm resistor, and we kind of see how these two things work together. Okay. So if I made this guy that same, let's make this guy say 10 volts of division. I'll move it down. Okay. And if I adjust this guy to that same 10 volts of division, I can kind of see how these two things relate. Right. I'm driving up the peak, and then I ripple down. I drive up the peak. I ripple down. You can see the relationship of it. Okay. So there's our power supply voltage, right? Now on the again on channel 1 here, I'm looking at, this is the ripple that is going right to our 50L6 output tube. So my probe, that's right at the primary of my output transformer. So if we go to look at that, right? Let's go bring this guy. Well, we're going to go look at audio circuits here in a moment, but. Let me go grab that guy over here. And let's turn our volume up. I think I'm on the wrong side of that here. Hold on.
Yeah, you want pin 4?
Yeah. Okay. Somebody will go back there. So it's kind of just tuning the audio on here a little bit, right?
A little bit.
But so this is where it can be really handy to be able to look at. Actually, you know what? It helps if I use the right probe. There we go. That's what I was doing. So you can see the audio sitting on top of that ripple, right?
Yeah.
But why doesn't it matter? Let's talk about the audio circuit. We'll talk about why it doesn't matter. Let's go back there. Okay. All right. So we're going to work back to that. So I started at the front end here. So sorry. Hang on for that. I know you're all waiting. Okay. So the front end signals. Okay. We got our RF input coming from the antenna here. That's going to be pretty small. You're not going to be able to see anything with scope probe done in the model. Okay? All right? You can probe the local oscillator. Like I said, Harry said you can kind of bring the probe near it to see that it's oscillating. Good enough. You actually want to measure the voltage. You're going to have to probably connect to it. Okay? It will shift. Okay? The frequency. In fact, if we go look at that, let's look at that. Let's take my probe over here. Okay, and I'm choosing the signal here, right? And let's go and, let's see, we're going to go look right on the way. Let's see, let's speed that way up. And let's go to trigger on the input there. There's my local oscillator signal. Okay, and if I tune it, see the frequency changing?
Yes.
Okay. Okay. It's just detuned a little bit because I was including that capacitance into where I was tuning. Right? Now I got to adjust the frequency just back again a little bit. Okay. So just be aware that that's going to happen, right? But that's okay.
So the probe capacitor is just added to the Brent slicer.
It's like exactly. It's like adding another trimmer to it.
Times one probe, you won't have an oscillator.
Right. Yeah, but too much, you might throw the thing out of the spot where it can't oscillate anymore. If that happens, just tune down, tune up to the highest frequency, so that if you pad that, it'll come down to a low frequency where it'll oscillate again. So if you really want to see what's oscillating. And you saw we're looking at here, about 10 volts of division. So we had a good 30 volts peak to peak there on this particular radio. I don't know what the variation is. You guys know better than I would how big that drive is, but that's kind of what you'd see. So it'll typically, the frequency will be, assuming you're tuned to plus 455, right? So you're going to be up in the 1 to 2 megahertz type frequency range. So running, in the order of a few microseconds of division to be able to see that. All right. Look at the output of the converter tube, right? This is where we're going to see the IF signal. And I think I've got, do I have a tap on this one? Let's see. Actually, I don't. I can look at the output of the IF transformer. Let's see. Okay, so now what am I looking at here? It's a pretty small signal, right? Because, like I said, the signal that appears here is going to be pretty small. And it's small for two reasons. One, it's the very first stage. We haven't amplified the IF yet. We're only just dumping this into the first transformer. And I put 10 picofarads across this capacitor. I just detuned it. Okay? And so now I can see the ripples. I'm looking at just a few millivolts of division over here now, right? 20 millivolts, 200 millivolts of division. But I can see that something's there. But I think it's okay if it's ugly. All right? That's not what we're trying to see here. Just want to see if something is there accomplished. Right? Mm-hmm. And the other part of the problem is that this thing being a trainer, everything's all spread out. My ground connection's over here, my probe's over here. I got a really big loop that's picking up 60 cycles. Okay, when you're inside the chassis of your radio, you're not going to generally see that problem. So the ripple here is more than what's really in the circuit. It's just being picked up by the probe loop. Okay, but don't be worried if you can't see it. Again, you guys know when you need to feed to ADC to kind of get a better view of things. Okay. The note here, probe capacitance will detune the circuits. It will detune and adjust your load. It will detune the load for the converter tube. Just be aware of it. Okay. So next stage is our IF. I went backwards. The next stage is our IF signals. So let's look at the output of the IF. What have I got there? It's going to be larger than the input. I'll probably, in this case, I'm going to still have some ripple because I still got this big loop. I'm not going to the detuning isn't going to be as bad in this case because the signal is larger. Okay. But looking at the detector output, we're going to actually be pretty good. We can actually see that. So let's actually go look at those two. And let's see, what do we say? For the IF out, I want AC coupling, about 50 millivolts of division, probably a little bit more than that in this particular case. Let's see.
Where's your sweep?
Just kind of I'm going to bring my sweep back down here. So a couple of milliseconds of division. Again, I got a little bit of ripple on here. So if I trigger on line, I can kind of stabilize that. See how the signal's tilted? It's because I'm looking at one portion of my ripple waveform. Okay. So by selecting line trigger, it's a lot better than doing that where things are bouncing around. I can actually get a better view of what's going on in the IF by looking at my line trigger. Okay.
It's causing detection. You can see your amplitude varying with audio.
Yep. So that's my IF stage. We'll look at the output of the detector, which is right here. Much bigger. Okay. Well, actually, I'm filtered there. Where I want to look is actually right here. Let's see. That's where I was. Which one did I pick? Well, I figured out one of these was actually.
One of the caps.
One of them is disconnected. So, and one of these is actually backwards. But anyway, we can go through and look at these things. So there's my audio actually sitting at the top of the pot here right now. Okay. Let's see. We could also look. Let's see. I think one of these I figured out was disconnected. There it is. That's the one I want to look at. So that's the looking at the detected output. Okay. So we're essentially the diode here is clipping the top half of my IF envelope. We're just looking at the audio variation on the bottom of that IF envelope. Okay.
What's key there is that you still have an IF envelope.
We still have an IF. It's just kind of choppy.
Once you go past the detector, there's a filter. It shorts out all the RF.
Right.
You only have the audio left.
So that's what we're looking at over here. Again, these are approximate settings. Play with them as you need it. A lot is going to depend on the signal strength you got going into the radio, that kind of thing. And then if we go take a look at the audio signals themselves, let's see, a couple of places we can go look, right? If we look at the drive to the grid of the output tube, the level there is going to depend on where you set the volume. So we can just go look at the top of the pot, and then we don't care where the volume is. All right. So and because we've got a couple of capacitors here, we're actually going to start stripping some of the IF off and just look at the audio. And let's bring that guy down here. This is one of the ones that's wired backwards. The top of the pot is the bottom of the pot.
Pot, okay.
Okay? So there's my audio signals. Okay? You can actually see that. And again, not going to depend really too much on volume here now. We're a little bit slightly different, but we're just looking at the audio signal now that we're going to pick off to go into the input of the tube.
Let me give you a little left RF, maybe it won't click.
That's okay. It's all right. Yeah, then we go measure the ABC and how much we're really driving that down. But they're okay. And then we can go look at other portions that we wanted to look at. We talked about earlier being able to look at the output here. Let's go here. So this is the output of the tube. Again, I got the audio kind of riding on top of that ripple, right?
So got that volume on here.
Okay, and I don't know if I bring the volume up, that'll go way up. So I got the audio riding on top of that ripple. So if I go down to line trigger, and now I can just see what's going on. But if I just want to see that voltage, the audio itself, let's bring on channel 2, set that to the same voltage reading. Then let's go probe that voltage. All right, there it is.
Okay.
Looks just like, let's see, that's my ripple voltage, right? Let's do a invert and add, and turn off channel 1 and channel 2. There's just the audio.
Yeah.
All right? You're not going to do this without blaring the radio, and then
Yes.
to see what that thing looks like. Okay? Now, we will do an add and subtract based on the scales. So if I change my vertical scale, it won't add or subtract rate. Okay, because that's all being done after the input attenuator and things like that.
Mm-hmm.
So if I wanted to look at higher volume levels, I have to turn both of these up to that same level to get the rate subtraction again. Okay? So that's a nice handy trick, since you don't have a differential probe, to kind of get rid of it. Now, why does that work, and why don't I hear the hum? If I got 4 volts of ripple there, why don't I hear that?
107 volts of audio, 4 volts in the scheme of things is pretty small.
It's not even that. But if I look, when I was listening to it down this low volume here, right? Just kind of go back down here. That's a fair amount. I got more ripple than I got audio. Why don't I hear it? So the key is that the tube is modulating its current back and forth, right? That current, the top is, if you will, the top in terms of voltage of the output transformer is bouncing up and down. The current going through the tube is creating a voltage across the coil. That whole thing is bouncing up and down.
Going all over the place.
So the signal, the ripple is common mode. It appears on both sides of the transformer. And the only thing that transfers across the transformer is the differential voltage across the coil. So the ripple effectively gets rejected because it's common mode to the transformer. So what we do with the scope of subtracting things is exactly what happens here to here. Which is why you're not hearing the hum from the ripple. Why it doesn't matter so much there. It doesn't matter later on because those voltages are kind of being processed all with respect to ground.
Mm-hmm.
This one's being processed with respect to the other side of the transformer.
Right.
Okay? So it doesn't matter so much. So that's why I say you can have a fair amount of ripple on that first beat plus before that next ballast resistor, but that's still okay. Okay? So let's use the difference measurement to actually measure what the audio is doing. Okay? Pretty cool?
Yeah.
Ooh. All right.
Why don't you probe the top of the volume control for DC and show them how that indicates signal strength?
Oh, sure. Yeah. So let's actually let's turn channel 2 off here. Let's turn all this add and invert stuff off. Let me grab.
This is a good measurement to make when you're doing an alignment.
All right. So let's. What I'm going to do is switch my coupling here to DC coupling. All right. If I go to ground, I can see where ground is. I can adjust ground to a spot on the screen and say, okay, with ground coupling at the input, that's ground. All right. So if I look out and now go to DC coupling, I can see my signal is going below ground. Okay. If we change our signal strength to the input of the radio, see how the DC is changing? The stronger you get in this, the more negative you go. That's your automatic volume control. All right. Because in the ABC circuit, that signal goes through another low-pass filter that effectively turns the average of that into a DC voltage that gets applied to the grids of the IF amplifier and the mixer.
You can go to that further and look at that and show them the line.
Yeah. Yep. Yeah. So let's actually go through that.
The flat line moving up and down.
Let's go over here. Let's bring this probe over. And what we're going to do is DC couple that probe, turn on channel 2. I'm going to put that ground up here as well. And we'll probe that guy there. So we can actually see where that voltage is. That's the flat line up there now. Okay, if I pull that away, let's actually make that a bit more sensitive.
You just look at the DC line.
Yeah, so, and there's your ABC, right? More signal strength, more negative bias on the ABC, cuts the gain down on those tubes. So it's like kind of a closed feedback system that adjusts the gain throughout the radio depending on signal strength coming in.
Yeah, if you're doing something like an alignment or something very crucial, the 10 meg probe will load the ABC line to where it won't work right.
Yeah.
It won't work the way it's supposed to.
Right. So it gives you an idea of where things are. It's a good idea to kind of look sometimes at the ABC to be sure that when you're peaking the IFs, you're also peaking the most negative excursion of the ABC at the same time. Okay, or you could defeat the ABC by shortening the ABC cap and then keeping the gain constant, so that the signal strength doesn't change the gain of what you're looking at. Okay. So if you're sweeping, sometimes that can really wiggle things around all over the place. So by keeping the ABC at some constant voltage when you're doing like this swept thing with the XY, you'll keep things a bit more stable.
Usually they tell you to sweep and just throw like a 3-volt signal on the ABC line.
There you go. Yes, that keeps the gain constant, and then that's not going to be changing along with everything else that's changing when you're sweeping through. So that'll make things a little less confusing to the radio and to what you're doing. Okay. So again, AC or D. So a couple of things here. Scopes give you a view of what's going on with voltage versus time. It can be really handy. Look at distortion, clipping, issues like that. Beware of ground. Scopes want to be connected to ground. Okay, some of these radios aren't too friendly about that. Okay, just be aware of it. Again, AC or DC coupling doesn't refer to the signal type. It could be handy, DC coupling here, to look at DC variations of a waveform, DC offsets of a waveform, but most of the time we're using AC coupling just to look at waveform shapes. Okay. IF and LO signals, you want to actually see the 455 kilohertz sinusoidal IF, or you want to look at the LO, a microsecond per division or faster, to kind of stretch that out and see the sine wave. For IF envelope and AF signals, a few milliseconds per division works well. Line triggering to keep the ripple stable. When you're looking at signals where there is ripple present, you just want to, okay, I know it's there, I don't care about it, let's keep it stable, now my waveform is just riding on top of that. Okay, so it's some handy ways to use a scope, to go play with these radios. And sometimes it's just fun, right? You don't have to be working on it, just look at it. I remember I bought my first scope, I was a freshman or sophomore in high school, and I had an electronics elective. And we had an old Allen B. Dumont Cathode Ray Oscilloscope current sweep scope that the school was throwing out. And I got it, and I put it in my room, and I watched Pink Floyd and XY mode on my scope in my room. So that's what you did with these things. But and for me, as a design engineer, analog design engineer, I visualize what's going on in circuits kind of the same way the scope visualizes signals. Higher voltages or higher elevation. So it's a very natural way for me to look at what's going on with signals. And with DC coupling, you can establish a ground is here, a voltage rail is there. You can see where your voltages are sitting with respect to a voltage rail. By clamping up against the rail, by banging down into, if I'm looking at a transistor circuit and collapsing, collector emitter voltage and saturating the transistor, you can see those things by seeing where things live within the supply rails. Okay. So it's a very visual way of thinking about what's going on with signals throughout the system. Anyways, that's what I have. Any questions? I really appreciate all your time. Yeah.
So if I'm looking at like a SAMS and it's got wave pictures in there to try to help you figure out what you're doing or whether there's something wrong, a lot of those parts of the set you're talking about, you're loading it down. Are those pictures assuming it's loaded down? Like that's the picture of this loaded down?
Yeah, generally they're going to have you look at spots that aren't going to be too much affected by loading.
Okay.
And they'll usually specify at the beginning of the SAMs, use a 10x probe,
right.
Use a probe with this input capacitance or less.
Right.
As long as you're adhering to that, then that's the expectation.
Right, okay.
And most of the time they're going to say, don't probe here, but probe there, because here the less effect is a low impedance port of the circuit or something like that.
Okay.
Exactly right. And I usually tell you it's so many volts per division, so many
Right.
microseconds per division. That's the wave shape you should see.
And what Matt's talking about, you can get away without a scope with radios. You get to television sets.
Right.
Yeah.
You got to have a scope.
If you get a television set and it says "Do not measure," believe it.
Right.
Yeah.
From
You say "Do not measure," it's not a kid. You're going to
second
destroy
angle is
whatever
not a
you
good
measure.
idea.
We're going to melt it.
You let the smoke out of the scope, and that's not a good idea. Yeah.
Okay, converting microseconds to frequency. Hertz.
Okay, great question. So 1 microsecond is 1/1,000,000th of a second, right? So it's 1 times 10 to the minus 6. Okay. So if you want to convert, let's say I want to measure frequency. Okay. Let's go do it. Let's take a look at my LO over here. All right. So let's turn this guy off. Let me go back to my 10 volts of division. Let's go look at my LO signal. Oh, with the right probe. How about this one? And move my ground over here so I get a little closer. Okay. Here's my LO signal. Let me go trigger on the signal itself. Wing it way out here. What's my frequency? Okay. Well, what we can do is say, all you need to do is count the number of divisions for a given cycle. And you can pick your convenient spot. Okay. Do I want to count from where I'm crossing the center radical, or I want to count peak to peak? It doesn't matter. As long as you pick the same spot from one cycle to the other. I'm going to cheat. I got cursors. Okay. Let's put my time cursors on here. So I can position one cursor, say, at this crossing point. Right? Say, okay, I'm going to call that 0. Now I count. Now I might want to say adjust my horizontal position to line it up right at a major radical. Right there. So now I can put my cursor over there. So I'm going to call that my starting point. And now I count over 1 division, just a little shy of 2 divisions, right? And I'm running at 200 nanoseconds of division, which is 0.2 microseconds. Okay, so that's 0.2. That would be 0.4, so I'm a little bit less than 0.4. I'm probably like 0.39. If I move this cursor over there, I can say I'm actually about 389 nanoseconds. 1 over 389 nanoseconds is the frequency. I'm going to cheat. The scope can do that for me. Right?
Oh, jeez.
Okay? So
Look at that.
2.57
megs.
Right. Okay? So that guy minus 455 tells me where I'm choosing. Right? Okay? Now, sometimes it's handy if you're it's easier to kind of see, like, I want to steepen up that edge. Now I got a number of cycles. What I can do is I can count over a number of cycles and say, okay, it's easier now. My error is going to be spread out over n number of cycles. So I can divide the error down. Okay, so I can say, okay, I count this out, get my time there, divide that by the number of cycles, then invert it, and I get the frequency. Okay. So that's a way of measuring frequency. Scopes are really, contrary to what you might think. Well, I'm measuring voltage with respect to time. Why isn't it the perfect tool to measure frequency? Well, the reality is it's not that accurate. Okay. Most of these analog scopes, at best, had about a 3% accuracy in the horizontal time base. And your eye is going to probably add another couple of percent to it when you try to measure where those crossing points are. So you're going to be off by 5, 6, 7% at best. Okay, it's not the best tool for frequency, oddly enough. Okay, it's good to look. Was that waveform really pure? Did it have some duty cycle distortion? Did it have some other kind of ringing or weirdness going on? You can see that stuff really easily. But measuring frequency, you're better off with a frequency counter or some other methods, like grid dip meter, or another receiver, to kind of tune into where everything's going. There's a lot of ways you can go do that a little bit more accurate. Any other questions? Nobody snore? You snore.
Believe me, everybody learned something this evening. Really appreciate it. Just a small token. This is from the AWR.
Thank you very much. Thank you. I appreciate that. Thank you very much. All right.
And again, you've got to subscribe to his channel, guys. All right? Again, really appreciates that. And you'll learn that much more on your own, at night, under the covers.
People are doing that by the YouTube channel. I don't want to.
The scope on your cover, you have it
Okay. All right, we are going to have an auction. All right, we have some nice radios outside. Come on out and participate in the auction.
That's all, folks.
Probably not this particular model.
Good night.